start.
Başladı mı şimdi?
Yes. Hi everyone. Sorry for this delay. And welcome to the fourth event in the series of Q project talks. Today, I am Onur Pusuluk. I will moderate the meeting with my friend Ecem. Ecem, hi. And in these meetings, our aim is to learn more about the ongoing projects on quantum technologies. And we don't want to listen these projects from the perspectives of PIs, but we want to learn these projects from the view of grad students. And today, our guest is Sean Deniz Thrasher from University of Edinburgh. And Sean studied physics of adiabatic quantum evolution during his undergrad and master studies. And now in his PhD, he started studying adiabatic quantum computation. Welcome, Sean, and sorry for this technical problems. And the stage is yours.
Right. Yes. So thanks for having me on here. So yes, I'm Sean, and I've just started my PhD in Edinburgh. And so let me get started. Okay. Right. There we go. So what I aim to do is, firstly, I want to introduce a class of quantum computers called analog quantum computers. And they're often not really discussed in the undergraduate course, but there's a lot of research going on in analog quantum computers, and they have some advantages for the near future. And I want to talk about how they're quite a natural platform for solving certain types of problems that can be cast as what's known as an optimization problem. And then I'll explore some open questions in this field. So first, let me just review a couple of concepts. So when I talk about an algorithm, what I mean is it's a list of instructions designed to solve a problem, and each algorithm has a complexity associated to it. And when I talk about an efficient algorithm, I mean that the complexity is sub-exponential. So as the input size grows and grows, then the cost of this algorithm, whether that be the runtime or energy, etc., must grow no worse than it must grow no worse than a polynomial, essentially. And so there is also this term that's used a lot in the field. These are called NISQ devices. It was first coined by John Preskill. And the idea is that we are quite a long way away from building large-scale quantum devices that are fault-tolerant. And that's because essentially qubits are highly prone to errors. They need to be kept isolated, but at the same time, you need to be able to control them from the outside somehow. And so this phenomenon called decoherence is almost, essentially unavoidable. So at the moment, we are essentially in the era of noisy intermediate scale quantum devices. So this noisy bit refers to how you get errors in your computation. And the intermediate scale means that we've managed to build quantum computers around the order of 100 qubits or so. Okay, now I want to talk about what analog quantum computers are. So for a digital quantum computer, the idea is that you essentially divide your computation up into a series of discrete steps, and you can represent these as gates. And what it does is it takes a quantum state and it changes it discretely in time. And this is the model that we often see and work with. Whereas an analog quantum system evolves a quantum state continuously in time, according to some Hamiltonian. And there's many examples of analog quantum systems. This is an example here. So this is a Josephson junction, and essentially you can encode your qubits as the flux here, and you have some external parameters that you can change continuously in time. So that's the key idea of an analog quantum system. You should be able to manipulate it continuously in time. So like building a scale model. So wind tunnel is actually kind of a good analogy to keep in mind. Just like how you can manipulate the parameters of the flow of air here continuously in time, you should be able to take a quantum problem in quantum mechanics that you're trying to solve and essentially tackle it on a scale model. So to summarize, you want to replicate the key features of some target quantum system in a lab on a system with parameters that you can manipulate and you can tune finally in time in the lab, and it's got to be a quantum system. So the overall roadmap here that I want to sort of lay out is that you can take an abstract problem that arises maybe in industry or physics or maths, turn that into an optimization problem, which you then can turn into an Ising Hamiltonian problem. This is a problem that comes from solid state physics, and I'll discuss what that is. And then the point is that you can simulate the Ising Hamiltonian on a quantum simulator, and there are algorithms written to tackle these types of problems. So are there any questions so far?
I think no, you can go on, Sean.
Okay.
And by the way, can we interrupt you whenever we have a question, or
Sure.
should we wait until?
Yeah, that's fine.
Okay.
It might might take some time. Anyway, yeah. So let me carry on. Okay, so now I'm gonna just illustrate with a particular type of problem that's studied. This is called the max cut problem. And the idea is that you've got a graph and you want to split the graph up so that the number of edges shared between two groups is maximized. So, I mean, for example, I could think of it as coloring, taking this graph and coloring in maybe red or blue. So if I take this to be red and I take this to be red, then, this is an edge that's shared between the two groups. This is an edge that's shared. This is an edge that's shared, and this is an edge that's shared, for example, and that would give me a score of 4, if you like. And the problem that I have to solve is what choice splitting the vertices up gives me the largest score here, essentially. And I'm going to show that we can formulate that in terms of an optimization problem. And there is an extension of this problem called the weighted max cut problem. So you also can assign weights to this. So this would count as 2 edges, for example. And so I say that Wij has a weight of 1 if there is an edge that connects node I to node j. So for example, W12 would be 1, but W13 would be 0, for example. Okay. Carry on. So I'm going to introduce the type of optimization problems that we'll be considering, but you can write this problem out as a function on a binary variable. So the idea is I can take this graph and I can represent it as a 5 tuple. So I've got a vector with 5 coordinates here, 5 components. And, let's say, so I colored this red and I colored this red. So I can write this vector out as 0, 1, 0, 0, 1, 0, 0. for example, right? So I can describe how I'm splitting this graph up by a vector, by a binary vector. And then I can find what this score would be, the number of shared edges, if I calculate this function. Okay, so I'll carry on. And the reason why this is a interesting thing to talk about is that it's known as an NP-hard problem. So essentially, for our purposes, it's a problem that is well, certainly tricky to solve on a classical computer. There is no known efficient classical algorithm that can solve this problem. Now, unfortunately, there's not really any efficient known quantum algorithm that solves this either. But the hope is that it can give us kind of a more optimal sort of overhead. It could still possibly solve it faster. An NP-hard problem refers to the fact that it's easy to check whether the solution that you've proposed is correct or not, but it's not necessarily easy to solve it as far as we know. Okay, so I'm going to introduce this type of optimization problems called QUBO problems. So the point is that I said that we can take a problem in, that arises maybe in an industry, right? And we can formulate it as optimizing a function. But the point is that this function is not going to be, something that's like that you'd see in calculus 1, for example. It's not going to be a nice polynomial which you can differentiate and find the critical points. It's going to be functions that are discrete and take in, ones and zeros into its input. And it will be essentially a polynomial in this of degree 2. So it's easiest to actually show you what it is. So essentially, it's a function that takes in, as I said, list of numbers, and there are constants alpha and beta such that this holds. The problem that you want to solve is you want to find an x that minimizes or maximizes this function. So going back to the max cut problem, for example, we gave an explicit form of f, and the question there was what input maximizes it. Okay. So now I'm going to talk about this really beautiful link between this mathematical problem of optimizing the function into a problem concerning Hamiltonians and energy. Okay. And the trick is that you think of the function itself as a Hamiltonian, and you think of the inputs that you feed in, so 0, 1, 0, 1, so something like that. Those will correspond to eigenstates of the Hamiltonian, so they will be written as qubits like this, and the output will be the energy eigenvalues of H. So here is H a bit more explicitly. So I take this X and I sort of promote it to a Pauli spin operator. I do the same thing here. And notice that this H will have the eigenstates X1 through to Xn. So all the computational basis is eigenstate for H. And these AIs and these BIJs are related to these constants here. Okay, so I'll carry on. Are there any questions so far? Well, please interrupt if there are any. Okay, and to make it clear, this superscript here means that we're acting on the ith or the jth qubit. And notice that now the expectation of H corresponds essentially to the output of F. So we've taken this problem of finding a maximizer or minimizer of F to finding a maximizer or minimizer of an energy. So the central task is you now have a problem Hamiltonian H that comes from some abstract computer science problem, and you want to minimize the value or maximize it. And this is a problem that's really studied, and there are many different approaches. I'm going to focus on approaching it from an adiabatic quantum computing perspective and a quantum annealing perspective, because these are analog. There is also, if you're interested, there's also variational quantum algorithms, which is another really nice and broad class of algorithms that are also very NISQ friendly. Yeah. So to summarize, we've got a problem that's hard to solve. Okay, obviously this particular problem is not hard, but you know, as there are more and more vertices, it gets really, really difficult for computers to solve. Then you associate that to an optimization problem, which then you associate to a Hamiltonian, which you want to effectively minimize. And so we looked at the max cut problem, but if you're interested in seeing more that can be formulated like this, I definitely recommend you check out this paper. This is quite an exhaustive, comprehensive survey of problems such as this, and I've just listed some examples that they've given ways to fit it in this manner. Okay, so where I'm heading is I want to talk about adiabatic quantum computing. So first, I want to introduce what adiabatic quantum physics is. What's the essential idea behind it? So before I actually talk about it proper, I want to give kind of a classical analogy. So imagine that we've got a harmonic oscillator and the parameters change slowly, right? So what I mean by this is specifically, you've got a time scale associated to the oscillations of your system, and you want to gradually change omega compared to that time scale. Okay, so if this is omega here, and this is your time, this is T, capital T stands for the period, then I want to make omega really gradually change compared to the time period. Okay. Then we can make kind of a neat but albeit hand-wavy argument. So you can write down the energy of the system, effectively the Hamiltonian, differentiate it, and then try to look at what happens to the effective change of this Hamiltonian. So if you integrate over a period, this term is negligible because omega changes very negligibly over a single period. And so we're left with essentially this differential equation, which means that over a time period, this quantity right here, if you take the energy and you divide by omega, then it's roughly constant. And this is known as an adiabatic invariant. So more formally speaking, this is what we essentially have. This is a big O of T. Now, let's go back to quantum mechanics. So this is telling us that for a harmonic oscillator, E omega is an adiabatic invariant. But if we sort of imagine going now to the quantum mechanical setting, it seems to suggest that this quantity here, so if I divide by omega, this quantum number is also an adiabatic invariant. So this is telling us that if you change the parameter slowly, the energy level doesn't change. So the key takeaway here is that if I have a quantum and I change the parameters very slowly in time, let's say that I start out in like the ground state, for example, then my electron will remain in that ground state with a high probability. So there'll be a very small chance of transitionings occurring. So now I want to formalize this a bit more, because this was very, 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 very informal. Let's talk about stationary state. So this is a review. So you consider the Schrödinger equation that describes how the state of your quantum system evolves in time. And we know that if the Hamiltonian is time independent, so if the Hamiltonian doesn't change at all, then you effectively get a time independent Schrödinger equation. So this says that you just have to eigenvectors of H. If you have the eigenvectors of the Hamiltonian, then you know that your system continues to evolve as that eigenvector. So this tells us that essentially, if your Hamiltonian doesn't change in time, if you start, then you remain in that eigenstate throughout. Okay. Okay, cool. So now suppose that instead you've got a vector. So imagine that we found a wave function such that this holds for all time. So imagine that we have something like the time independent Schrodinger equation. Would this be a valid solution for the Schrodinger equation? It would not be. So to actually study this, well, so first it's worth just discussing what an instantaneous eigenstate is. So we say that a phi is an instantaneous eigenstate of the Hamiltonian at time t if this equation holds right here. So whenever I talk about instantaneous eigenstates, I mean this. So let's talk about a two-level. So I want to illustrate the adiabatic theory in terms of a two-level system. So imagine I've got a two-level system, right? So I'm just trying to visualize it. A two-level system, right? And so this evolves in time, and phi 1 and phi 2 are essentially your instantaneous eigenstates here. So these are essentially your energy levels. It has energy E1 and E2. So what will the dynamics look like? So if I plug this into the Schrodinger equation, then I get this right here. Now, let's try and actually see through what is this saying? What is this telling us? So first of all, imagine that H is not changing in time. Then you'd essentially end up with just this bit. This would be 0, this would be 0. So all of these would be 0. And so you would recover the time independent Schrodinger equation. But if your Hamiltonian is changing in time, then you get essentially, well, this is going to be essentially your error term. So notice that this is telling us that the smaller the energy gap is, so E2 minus E1 is like your energy gap. The smaller it is, the more likely you are to get a transition. And the faster H changes over time, the more error you'll get. Okay, so if my energy levels look like this, then here I would have very little chance of transitioning. I'll remain in my ground state, but then when I get to here, I might do a transition because this gets rather small. And likewise, if my Hamiltonian, so if the energy levels change very suddenly, then I could get a shift, a transition. Okay, so the statement here is that if you start out in an instantaneous eigenstate, then there's a high probability that you will remain in the same eigenspace. Okay. Okay. There we go. Now, so we imagine that we're starting at time. So now to connect this to, we're going to talk about how this is related to quantum computing. I'm going to imagine that I start out at time t equals 0 with some initial Hamiltonian, and then I end up at a final Hamiltonian. Okay? So this is the picture that I want you to have in mind. Okay? Now, the adiabatic theorem stated more precisely says that, so this right here is the error. Okay? So this is the error in this adiabatic approximation. It's bounded above by this. So this is saying that if you make the change more gradual, then you have less of a chance of transitioning, going from the ground state, for example, to a higher energy state. And it's also that the longer you evolve your system, then the more chance there is that you would make a transition. Okay. So are there any questions at all? Are you happy? Check the chat. Okay. Okay, I'll carry on then. Okay. Okay. So this is a more precise statement. So this is what you'll need when you're when you're actually studying adiabatic quantum computers. So essentially, a more precise way to bound the error here is that essentially here, so this looks rather complicated, but this is saying again that if your energy eigenvalue gap gets very small, then you'll get potentially a really large error. And this P right here describes essentially it's the projector. So it's saying again, it's related to how fast the Hamiltonian is changing, and so you don't want the eigenspaces to change too fast. And then here again, you want the total time to be as long as possible. Okay, and I just want to demonstrate this with a two-level system. And so imagine that I have a Hamiltonian like this. Then so what happens is if I start here, I end up going through like that, right? So this is so 0, 1, for example, and then this is the ground state. So 1, 0. Okay, so just erase that. This is 1, 0. So if I start here, then I end up crossing over like that. Okay, and if I start here as well, I cross over like that, and there's no probability of me transitioning. But now if I make a gap here, I'll end up staying. So if I'm in the ground state here, I'll end up staying in the ground state with a high probability. And the point is that if you make this gap smaller and smaller, then the chance of you transitioning gets larger and larger. And if you make change more slow, so if it looks like this instead, then there's more of a chance of staying in the ground state. So just to compare, so if I start here, I end up here. If I start here, then I end up here, but there's a small chance of going over here. And then if I start here, then I'll remain in the ground state with a high probability. And it's possible to derive exactly what this probability is. Okay, so just to summarize, if you have a time-dependent quantum system, you can have transitions occurring, and if the Hamiltonian changes stuff, then the and the energy gaps are large enough, then you stay in the same eigenspace. Okay, so now I want to talk about how we can apply this to adiabatic quantum computing. So as I hinted before, you want to start with some initial Hamiltonian and end up in a final Hamiltonian. And you do it with a function here. So the function has to be 0 at time t equals 0, and it has to be 1 at time t equals 1. And S here is defined to be the ratio of the time to the total time here. So, okay, now all of this was rather abstract, so I'm going to connect it back to what we were discussing before. So remember how we said that so for the max cut problem, if we have a solution to the max cut problem, then that corresponds to an energy minimizer of this. So it makes H psi small. So essentially the ground state of H minimizes F. Okay, so I've connected these two worlds here. I've connected this quantum mechanical world to the world of optimization here. So we essentially want our system in the ground state of HF somehow. Because if we can do that, and then we do a measurement at the end, then we can read off what the answer should be. And so obviously it's difficult to know what the ground state of this should be, because if you did, you'd have solved the problem. So what we do is we imagine we start out with a Hamiltonian like this, and this has a ground state, which can be easily prepared by a Hadamard gate. And the point is that if I go from this HI, this initial HI to this final HF, then this ground state that I start off with will be forced to the ground state of HF, which is the solution. So this is the key argument here. And this is what the time-dependent Hamiltonian would look like. But the problem is that you might have energy crossing. So remember how we said that the accuracy of this approximation depends on the energy levels being separated far apart. So the adiabatic theory might not be valid. So you have to check this. And there might be more robust versions of the adiabatic theorem that I mentioned. Okay. So so let's now talk about there's a related type of quantum computing called quantum annealing. And the idea is the following. So again, we have the same problem in our hands, right? We want to minimize energy, right? Because that will solve the optimization problem. So the question is, how can we minimize energy? So what you could do is imagine, you're some hiker on this. This is like a mountain, imagine, and you're a blindfolded hiker and you want to find the very bottom here. So what you could do is you could try to follow the direction of the force. So try to follow down. That's known as a gradient descent method. But the problem, you could get stuck at a local minimum. That's not a global minimum. So you might get stuck over here, for example. So you follow the force of gravity down and then you stop when there's no force. So the algorithm can get stuck in a local minimum, as we said. So what you could do is you could essentially take random steps, left and right, back and forth, and then you decrease sort of this fluctuation, and what will happen is you'll end up settling to the minimum. So this is sort of a scheme of what's happening. So this could be your cost function, and as you reduce your temperature, effective temperature, you'll end up at a global minimum. So now the approach in terms of quantum mechanics is to introduce a tunneling probability instead. So what you do is essentially, instead of going up and down, you tunnel through. You use the fact that you can tunnel in quantum mechanics. Okay. And so, okay. So the idea then is that you start off with this at a very high value, and then you decrease it. So you're starting with gamma at a high value, and then you decrease it, and you want to decrease it polynomially for it to get adiabaticity. Yeah. And you might wonder why we're doing it like this with the sigma x. So the point is that observe that sigma x flips a qubit from 0 to 1, and it flips from 1 to 0. So if you start off over here, if this corresponds, for example, to a spin up, and I apply sigma x, then I'll end up going over here. So it's like I've tunneled through. Right? And so notice that this is related. So if I take this simple example here, so a simplification of this example, this looks like a Landau-Zenner transition. Okay, so I'm going to now talk about sort of the how this scheme of quantum annealing is used in the industry, and a very prominent platform is the D-Wave company. So they've made these quantum annealers, these devices I've just talked about, this thing that can device that can allow you to tunnel through these energy barriers and find the minimum of an energy function, and therefore solving a problem, an optimization problem. So they managed to make quantum annealers available since 2011, and they built devices. So this is a picture of it. They built devices with 2,000 qubits, right? So they managed to build with 2,000 qubits, and they've managed to also essentially make connections between the two sigma I, sigma j terms in your sum, right? So this is represented by the connections over here. And you can tune these over time. So you can encode the optimization problem. But the problems, there's a few problems. So first of all, the qubit quality is quite poor currently, and the connectivity is quite limited. And so there's a debate as to whether, this effectiveness of there's even an effectiveness of quantum annealing. So I personally would be interested in going down the route of, sort of probing this more on a theoretical basis and trying to find sort of theoretical guarantees, because quantum annealing is known as a heuristic method, right? So that means that essentially there is no theoretical bounds on the performance. Okay. So finally, as the final subject that I want to touch upon, so there is this nice equivalence between digital quantum computers and analog quantum computers, and I'm happy to talk more about it later on if you want me to. But the main idea I want to get here is that you've got this Grover search algorithm that happens on the digital quantum computing platform, right? That's been written on the digital quantum computing platform. You want to find a marked object, and you can write an analog. You can write an algorithm that can be run on an adiabatic quantum computer. So the choice of the final Hamiltonian is this, because the ground state of HP is the marked item. And this is what we start off with, because you can prepare a plus state with a Hadamard gate. But the issue is that if we make this choice right here, so if we choose to evolve our system like this, then we find that the runtime grows linearly in the size of qubits. And this is actually not at all an improvement compared to the classical algorithms that exist. The Grover search algorithm for digital quantum computing has a square root n. So the point is that you need to make a different choice for the function that takes you from the initial state to the final state. And so another possible open question is to find a systematic way of determining what these f should be to recover this the quantum advantage that happens in digital quantum computing. Okay, so for a generic problem, this is tricky. So just to summarize the open questions, because we're still in the NISQ era and you've got still a lot of noise, it's an important problem to develop methods for demonstrating quantum advantage on analog quantum computers. And then, just as I discussed here, another separate problem is, what is an optimal choice of a schedule? What is the optimal choice of the function that takes you from initial to final Hamiltonian? And then final third problem, which we discussed earlier, is to find better results for quantum annealing. So to summarize, so we discussed quite a bit. We talked about how adiabatic quantum computing is a rather natural platform for some hard problems. and that it's a different paradigm of quantum computing altogether compared to digital quantum computing, and that challenges arise in demonstrating quantum advantage, and there are challenges in the actual quality of quantum annealers, and there's this theoretical challenge of finding the optimal choice of this schedule that takes you from initial to final Hamiltonian. So that's all that I had for my talk. We'll check the chat if there's any questions.
Thanks a lot, Sean. I think in the chat there is no question, but our participants can unmute themselves and ask their questions directly if they have any.
I did get a question in the chat, but to be honest, I don't have any idea. Is it possible to build a quantum qubit gate with a ballistic conductor instead of a superconductor? I'm not sure what that is. Do you have any insights into that?
No questions? Then let me ask a few questions, Sean. Maybe in that time others also can prepare some other questions. In quantum thermodynamics, there are some protocols called shortcuts to Adiabaticity.
Right.
In these protocols, they provide some contra-adiabatic driving, or let's say transitionless quantum driving. And is there a possibility to use such tools in adiabatic quantum computation? Because for the adiabaticity, we have we should have a slow evolution. But if we can use these shortcuts to adiabaticity protocols, maybe we can make faster computations. Is it possible?
Interesting. I haven't heard of the shortcuts to adiabaticity. I mean, in the literature there is quite an intimate connection with thermodynamics. There's, they study I know that in the thermodynamic limit, I keep coming across there's this fact that you get, so when you have this particular choice of schedule that we talked about, well, going from the initial to the problem Hamiltonian that I discussed here, in the thermodynamic limit, I'm aware that you can get sort of, they call it phase transitions, but essentially you get crossings of energy level, and that can cause essentially issues because the theorem is not valid. So I don't know, maybe if you use this shortcut, you'd have to really check what happens to the energy levels. You need to make sure that it stays bounded,
I think the motivation behind these protocols is to avoid level crossing by including some extra interactions. But and in the thermodynamic cycles, you have some adiabatic strokes, and they take some time. And people use these protocols to make faster thermodynamic cycles. But I don't see any application in quantum computation. And
I'd love to discuss.
I just want to mention there is some technique to make this adiabatic quantum computation faster, and there is some adiabatic diabatic quantum computation, and also I saw some technique like contour adiabatic, and this kind of technique is normal, but maybe we need more analytical form if you want to talk about how they want to make this process a little bit faster. But yeah, some group at the moment working, and also I know Professor Nishimori in Japan working in this kind of computation with adiabatic, and also additional term to your presentation. In fact, they have an initial Hamiltonian and also Hamiltonian, but they have a midterm, and they work on this midterm to make all of this adiabatic computation faster. This is a way, and I think if you want, I can send some article from Professor Nishimori about this kind of computation.
Yes, yeah, please do.
Okay.
I can put my...
I will send it in the chat box.
Okay. I mean, yeah, I can put my, I'll put my... Just put my email, so...
By the way, there's a question from YouTube from Jonathan Wainrich.
Right.
He says that very nice and clear. And interpolation, are there any results if we use sine or cosine instead of linear?
Yeah, I think what I was looking. So yes, this just general this general sort of paradigm of wow, yeah, really good question. Yeah. So in my master's actually, so I looked at just generally where your phase space is essentially periodically changing in time instead. So so instead of going sort of, you know, from initial to final and that's it, you sort of repeat overall. And so essentially that would, I guess, you know, correspond to like a interloping Hamiltonian there. But with that, you'd have to sort of decouple your subspaces and, you know, couple them back in periodically. But I don't know if that made any sense to anyone. Yeah, I mean, I mean, just generally, yeah, there's nothing stopping you from using sines and cosines anyway, I suppose, as long as these, you know, these conditions are met and, you know, this approximation here is valid. But yeah, it's actually an interesting sort of paradigm with doing this periodic coupling and decoupling in space, and I wonder maybe that could be a way to speed up this process that we're talking about, or, you know, sort of a shortcut to adiabaticity that's not really explored in the literature as far as I'm aware.
Is there any other question from the audience?
I just have a question about the kind of problem you can encode. In fact, you know, generally we consider all the problem which is quadratic program in the computer science. We can solve it with simplex, for example. All of this program which is quadratic, we can with all the constraints, you know, and the problem maybe had a lot of constraint, and we can in fact encode all of them in an unconstrained quadratic binary optimization form, and finally we change all of them to Ising model. I just want to add something. Maybe I want to say to the audience, adiabatic quantum computation and all the variation like quantum annealing and these kind of things, because they focus on the discrete problem, it seems they are not very powerful. But if we want to say generally, quadratic program problems can be completely solved in this way, and there is a broad range of problem we can solve with this analog or also digital version. It's not important, but I want to say, okay, it seems the formulation is simple and also we can use it easily, but in fact we can solve a lot of good problem if we a little bit search about the quadratic programs, and I'm sure the computer scientists are more interested in this kind of things because physicists are not familiar with a broad range of problem which is discrete and we can solve it with adiabatic quantum computation. But the method is powerful and many scientists at the moment working in this field, and the results are also interesting. Maybe we can show some good article in this way to some young scientists who are interested in this kind of fields. But thank you for your presentation. It was very nice and
thank you for your contribution. Yeah, please do send me the articles. And
yeah, absolutely. I searched it, but I couldn't find at the moment. But I will send to this email.
Yeah.
Thanks so much.
Yeah. That's what's nice, I guess, about studying problems that sit at the interface of, so many different subjects. That's what's quite beautiful about it,
And Sean, let me ask one more question about adiabaticity. Have you heard about protective measurements proposed by Yakir Aharonov and Lev Weidman?
Yeah, projective measurements.
Not projective, protective measurements.
Protective. Oh, I don't think so, no.
I think in this measurement protocols, these are weak measurements, but you perform these measurements in an adiabatic sense. And as far as I remember, their proposal was that they are able to measure the expectation value of an observable in a single copy system. And also there are some other type of measurements called weak measurements, again proposed by the same team. But here adiabaticity makes the measurement more powerful. And have you heard anything about this? And there can be any room to measurements in adiabatic quantum computation?
I have not. I guess then you have to worry about they have open system dynamics then at that point, I guess, right? And definitely, that's sort of the topics I'm gonna go to next. So it's a measurement. So it's you perform the measurement in an adiabatic sense, and it makes it more robust. That's interesting.
I think the first claim was to measure the wave function. This was the first paper by Aharonov and Weidman. And I think a few years ago, the first experimental realization also published. But I think this kind of measurements are not so popular in the literature. This is why I am asking.
Right. And I mean, is this is it a scalable sort of method as well? I mean, I suppose it is. You're just manipulating. I mean, I know that there's I guess if it could fall under measurement-based quantum computing. Okay. I mean, that's quite I know that there's quite a big field of measurement-based quantum computing that allows you to manipulate your system using measurements there, and I suppose this would be a way to manipulate your system. It's an open system. Anyway,
Yeah.
I'm just rambling. Yeah, that's yeah. I'd
And
love to look at the articles.
I can share the articles with you. And one more question here. We use the closed system dynamics
Yeah.
and find the minimum of
Yeah.
the energy, and because we map our optimization problem into this process. Can we also do the same for an open system dynamics by mapping the
Yeah.
problem into the minimum of free energy?
Yes, so I think there's a general rich literature in the open system dynamics. I admit I haven't quite explored that yet. But I mean they use open system dynamics to also show sort of the error tolerance of adiabatic quantum computing. I'm not familiar with how that would affect the energy landscape, though.
In the machine learning literature, I think there are some applications called Bosman machine algorithm. And my question is that can we do the same here with quantum computation? But I think in this way, in the open system dynamics, we don't need to use adiabaticity. So if we can do analog quantum computation in this way, we can end up with some faster processes. But
what processes?
Instead of mapping our problem into a closed system dynamics, if we move on to the open system dynamics, we don't need adiabaticity for timealization, for example. So in this way, maybe here the adiabaticity is the thing that takes time.
Right, interesting.
And is there any question from the others?
I just put a article there about the shortcut.
Yeah.
But you can also check all the shortcut of adiabatic in the Google Scholar. There is a lot of kind of shortcut, and I think it's interesting if you want to know a little bit more about it.
Yeah. Thank you. Very nice. So shortcuts.
And let me ask my final question, Sean, because nobody asked question than me and Emma. Here, we do an optimization, but we call it as computation. Can we do all the computational tasks by using such optimization methods? Why we call it as adiabatic quantum computation, but not adiabatic quantum optimization? Here we solve an optimization problem.
Onur, you can do all the possible. In fact, this method is universal. First of all,
this is the question.
This is the universal quantum computation. An adiabatic version is, in fact, analog version of all the digital form we have. For example, you can do Shor algorithm, Grover search, Bernstein-Vazirani, all the possible things. Circuit based, you can do all the things in the analog form. So this is absolutely a universal form, and because of this, we can study adiabatic quantum computation. But the best use of this method is at the moment optimization, because we cannot find, at the moment we need to find some use cases for quantum computation. But at the moment also we need to improve hardware and at the same time improve the software, and this is an interesting challenge, because this is, I think this is in the classical story of computing, we someday we had hardware, and also it was easy, we do all the computation. But here in the quantum side, the story is completely different. We need also some fault tolerant quantum computer, and at the same time we need to find some use cases for this hardware. So yeah, a bottleneck at the moment is both hardware and software here. It's interesting, I think.
Thanks a lot, Ahmad.
Yeah, and quantum annealing is not universal as far as I.
Quantum annealing is not universal because it's meta. Yeah.
Right. Yeah. Meta.
Yeah. Here, the Adiabatic quantum computation is heuristic. Yeah. Thank you so much, guys. It was a nice talk.
Thank you so. Yeah. Thank you so much.
And let's ask once again if there are any questions from the audience. Not, let me check the YouTube also. There are some things from YouTube, but no questions. Thank you very much once again, Sean. It was a great talk. It was quite informative. And Ecem, are you here? Would you like to say for closing?
Well, I also would like to thank you to Sean for this beautiful presentation, and I hope you enjoyed it as well, I guess. So yeah, thank you so much for our participants too.